MOSFETs on the same integrated circuit chip. So Moore's expected that roughly, the number of MOSFETs, the number of transistors on a chip will be doubled every year. And this happened until today, or maybe tomorrow, or maybe 3, 4, 5 years from now. This is the case. But later on, this will not be the case, as we will see very soon.
Wasn't it 2 years and then it was reduced to 18 months?
Yeah, it's okay. I said roughly. I didn't say exactly, just roughly. We don't want to argue about this, because it is also not 18 months, not 2 years, not 1 year. It is roughly every 1 year it will be doubled. Roughly it will be doubled every year. Of course, this is what the advantage of the scaling down, and this is also a very important observation. Without scaling down, doing the job of a single PC microprocessor chip, operating a billion transistor at 2 gigahertz, which is very commonly quite available today, using the 1970 CMOS technology would require the power output of an electrical power generation plant. Now this microprocessor is working from a battery this size. Thanks, alhamdulillah, to the scaling down of the transistors. Without scaling down of the transistor, we cannot achieve this. We would have to use the power of an electrical power plant to supply our microprocessor. Now let us go to what is the MOSFET. I am sure, most of you know what is this, but just to make things clear, this is the MOSFET, very simple structure. Source, drain, substrate, it has a width, and it has a length, and there is a gate, and there is an oxide here. And as you know, we have to apply a voltage, a proper voltage to the gate, between the gate and substrate, in order to establish a channel here. And once a channel is established, we can apply a voltage to the drain, between the drain and the source, and attract the electrons which will be in the channel and generate the current. This is the MOSFET, nothing else. But there are two very important parameters in this structure. The L, the length of the channel, and its width, the width of the channel. The length of the channel and the width of the channel. And of course, the thickness of the oxide, As you probably know, the relationship between the drain current and the gate to source voltage in the saturation region is this one, K equal to Vg H minus E threshold squared. But K itself is a constant which depends on the oxide capacitance. The oxide capacitance depends, of course, on the oxide thickness. Epsilon T, as we make the oxide thickness thinner, notice this, as we make the oxide thinner, we will get larger C oxide. And as C oxide is larger, K will be larger, and the current will be larger. And getting a high current is always good for us, because this means that we can operate our transistors at higher speed. In the meantime, also, K is proportional to W over L. So the smaller the L, the larger will be K. And the larger will be K, the larger will be the current. Again, we are, or the people in the industry are fighting to reduce the thickness of the oxide, and reduce the length of the channel, and reducing the length of the channel. And the whole story was around this. How to reduce the thickness of the oxide and the length of the channel without, of course, being hurted by the consequences. Because reducing the thickness of the oxide automatically means that the electric field in this area will be very high. And eventually the oxide may be broken down. And reducing the length of the channel means that, we will come to this later on, means that the formation of the channel will not be under the full control of the gate. It may be also affected by the drain, and it is also always necessary to avoid this. We want our channel to be under the control of the gate, and only the gate. Otherwise, all these equations will be wrong. Because as you see in this equation, there is no VDS. VDS doesn't appear in the saturation region, by the way. In other regions, VDS may appear. But in saturation region, we need this equation, and this equation doesn't contain VDS. the gate. Remember this. When it started at the first time in the early 60s, the length of the channel was 10 micrometer. Today, it is common practice to have 40 nanometer. It is quite normal to have 40 nanometer. You can see it's a big difference. And the essential physics, the physics which led to the equation which I mentioned before, remained almost the same. No change in the physics. As you know, we apply a voltage at the gate. This will attract right voltage at the gate. This will attract the minority electrons in the substrate. This will be brought to the surface of the substrate, but they cannot proceed because there is an insulator. You are imagining what I'm saying? And a channel will be established. Then the relationship between the current in the channel and the voltage between the gate and the source is a square law which I have mentioned. This square law remains the same over the years. For about maybe 50 years now, this square law characteristic remains the same because the structure remains the same. But of course, things are coming to change. Problems of scaling down, as I mentioned, the electric field inside the oxide will be very large, and eventually the oxide is very thin and may be broken down. Heating up the transistors, if they are scaled down and they are placed together, very close to each other, in just a chip of much lower than this area, they may be heated. And this heating may affect neighboring transistors, and as such, the operation of the integrated circuit may not be reliable. These are the disadvantages of scaling down, and of course, as I said, the classical physics which led to this square law equation doesn't work anymore. Why? Because when the distances are too small, electrons may start to change their mind. Rather than waiting until a voltage attracts them and move smoothly, as we know, they may start to think in a different way. They may start to do tunneling. Tunneling يعني ايه؟ يعني نط. يعني بدل ما الالكترونات تمشي كده بهدوء عادي، فولتج بيشدها وهي تنشد ورا وتمشي، تبتدي الالكترونات تنط. ازاي تنط؟ This is a simple explanation for this phenomenon. The electrons today are not considered as particles as we used to do long ago. They are considered as waves. A wave with certain energy. If a wave with certain energy faced an insulator, this is an insulator, the wave will not stop. It will continue. It will cross the insulator and appear at the other side with lower energy, yes, but it will appear at the other side. This phenomenon we call it tunneling. And it will take place, of course, if the width of the insulator is too small. Because electrons will not wait until we apply the right voltage and attract them. They may take other decision. They may start tunneling across the insulators. And as such, they may produce leakage currents. So rather than electrons come to the surface of the substrate and stop there because there is a thin insulator, or silicon dioxide, which prevents them from proceeding, they can jump. And they can tunnel. And as such, there will be a gate current. And the major advantage of the MOSFET, which is having zero gate current, will be lost. You know this. The major advantage of the MOSFET is having a zero, almost zero gate current. This will be lost. Now the leakage current will be large. Remember this expression, the leakage current. The leakage current, the current which will proceed from the substrate to the gate and make the gate current not almost equal to zero. And this is a great advantage which we want to preserve. We want to keep the gate current equal to almost zero so that we can get high impedance and so on. So this is the phenomenon of tunneling. Scaling techniques. How the scientists start to go around these problems? Remember that we want to reduce the length of the channel. We want to reduce the thickness of the oxides. But there are problems coming from this. But the end result is we want to increase the current. Increasing the current is always good because this means that we can have faster device. How the scientists got around this? They added, first thing, they added nitrogen to the silicon dioxide. The silicon dioxide, if we add nitrogen to it, this